I'm now going to discuss the distributions, basically under the broad heading of distribution theory. In this presentation, I will first give an introduction about distributions, then get into the various types of distributions. Principally, there are two types: the discrete distribution, data distribution that deals with just discrete data, and continuous distributions, distributions that deal with continuous data. And for every distribution, there are parameters, usually two. One is a location parameter, and another is a shape parameter. And these parameters vary from distribution to distribution. So the basic difference from one distribution to another is the parameters of the distribution, which consists of both the shape and the location, and as well as the distribution and the probability distribution function and the probability mass function. Then I will be discussing discrete distributions in detail, on how it is estimated, the various types of discrete distribution, the important ones, and how they are to be calculated and used in real life situations. In the study of statistics and probability, the number of distributions that we encounter and their respective formulas can become very overwhelming. So there are a lot of distributions, and the formulas are also very complicated. But one should not worry too much about it, because now there are programs, even Excel can handle distributions, and more sophisticated programs like R and Python can handle it much more efficiently and makes the job of the analyst much easier and reduces to just interpreting the results. It is important to note that if we know a random variable follows a defined distribution, we can simply use their formulas for mean or variance, or sometimes even their other parameters like their probabilities and cumulative probabilities to calculate these values. So basically, to fit a distribution, you should know the values of the parameters, and you should also know the probability mass function in the case of discrete distributions, and probability density function for the continuous distributions. It is difficult to define the distribution the variable follows. So a priori, just looking at data, it is very difficult to calculate to calculate the mean and variance using. It's very difficult to calculate the parameters of the distribution unless you know what the distribution is. And then once we know what is a distribution, then we can use what is called as a probability mass function, PMF, for discrete distributions, and the probability density functions for continuous distributions, to be able to predict those, to estimate the probabilities for the distribution. Now, what is a random variable? A random variable is a measurement that is usually denoted by a variable such as x. It is a measurement, it's an observation. In a random experiment, a variable whose measured value can change from one observation to another is referred to a random variable. Let me give you a very contemporary example in Excel. Now I will open Excel and take you to a data which is quite recent in origin. This data is available in the net. You can always go and get it. And I will take this data which is on COVID. Okay. So the number of deaths, two deaths. So the number of deaths, it can be 0 death, 1 death, 2 deaths, 3 deaths. 3 deaths becomes a random variable. So this is a random variable. So there will all be zeros in the initial phases of the data. So as the data progresses, the death number of deaths also, you can see the number of deaths initially were not very high. So I'm just giving you an example of a random variable. So you can just see there's some spurt in China during the beginning of it was from 27th of January. So before that, the data is virtually not very important, because there is no, these all values are zeros. There are some deaths. Okay. Right, okay. So okay, we'll not disturb the data, so you got data. So this is a random variable. So number of confirmed cases of this thing on a particular date. So you have 1 and 4 and all. So this becomes a random variable. Okay. So a random variable is a variable whose measured value can change from one observation to another and is referred to as a random variable. And from this random variable, you can find out what is the probability there was one death in a day, what is the probability there were two deaths in a day, what is the probability there is three deaths in a day. Okay, so used to quantify the likelihood, so we can find out the probability. What is the likelihood of one? So that is also called the probability. So used to represent the risk or uncertainty of an event. So we can also use it in this condition to find out. But the probability tells us what is the risk, or what is the probability that one person will die, what is the probability that two people will die a day, what is the probability that three people will die. It can be interpreted as a degree of belief or relative frequency. Now, if you want to find out what is the probability of a particular event happening, then we usually use a distribution. Okay, and what we call is a probability distribution. So what is a probability distribution? A probability distribution is a mathematical function that provides the probabilities of the occurrence of various outcomes in an experiment. There are two types of random variables, discrete and continuous, and depending on what category the random variables fits, we calculate the mean, the variance, and the probability from this distribution. Now, what are the practical aspects of distributions? For a data scientist, every probability distribution you would need to work with can easily be visualized and we can work with these distributions. So first we need to plot the distribution, and then you decide to go, you take the next step of going about and working with it. So we are able to generalize random variables that follow specific distributions and visualize their distributions graphically. To become to become easier to recognize, random variables, probability mass function and probability density functions with practice using the random variable. So once you have the probability mass function and the probability density function, it becomes easier to estimate a regression, a distribution. Being able to quickly recognize the various distributions in practice is advantageous, as it can save a lot of time and help statisticians and actuaries become more efficient. So you should be able to recognize distributions. So what is the learning objective of this class? After the study of this presentation, you should be able to do the following. Determine the probabilities for discrete random variables from the probability mass function, and for continuous variables from the probability density function. So what you need to note over here is the probability mass function pertains to discrete variables. Probability density function pertains to random variables. Okay? And you should be able to find out the cumulative distribution function in both these cases. You should be able to calculate the mean and the variances for discrete and continuous random variables, understand the assumptions of each of the probability distributions presented, select an appropriate probability distribution to calculate probabilities in a specific application, understand the concept of a standardized random variable, use the tables for the cumulative distribution function of a standardized normal distribution to calculate probabilities, the approximate probabilities for each of binomial and Poisson distributions, interpret and calculate covariances and correlations between the random variables. Then you should be able to calculate the mean and variance of a linear combination of random variables, approximate means and variances of general functions of several random variables, and understand the statistics of the central limit theorem. So this is basically what you'll be expected to know at the end of this course. And now I make my presentation on what is a discrete distribution. Now before I'll go back to this data. Now here you have data, on COVID on different days. Now the amount of, this is a random variable, because this value of 2 does not depend on this value. That is what you mean, that the variable is independent. It's called an independent random variable. Now it is zero confirmed cases. It's nothing to do with the 2 confirmed cases earlier. So that is why you call it a random event. So now here, this is discrete data because it takes only discrete numbers. It doesn't take fractions. You can see this. No, there were a whole lot of zeros, before suddenly you got 444 on the 22nd of this thing. So what I will do is to make it simpler, because to avoid too many zeros in the data, I will remove this. Okay, sorry. So we will look at when the coronavirus outbreak really took place in a very big way in China, in a place called Hubei. So the data prior to that, I will just take it out because the numbers are very small and may affect. Of course, it's only for learning. So okay. 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 Now here's my data, and here's my confirmed cases of coronavirus. Okay. Now I'm going to fit this into a distribution because I can understand this better. To fit into a distribution. To fit it into a distribution, I first have to know what is the minimum value. Obviously, it is 0. Because there have been days when there have been no incidence of. Okay, so we have 0. So I think I will look at deaths. I will look at deaths. Okay. And I've got the minimum is 0. And I will also get a maximum of the same column. I've got a maximum on a day. The death went up to as high as 5,000. So when I want to make this into at least about 20 class intervals, so class intervals have to be decided using maximum minus minimum within brackets divided by 20. So the gap will be around 273. So I think that graph, I should make it a little bigger. So I will make it 50 class intervals. So the gap is 100. So less than 100. So I think I'll take it even 100. I'll take 100. So they can capture low values. Okay, 100. So my gap is 50. So I will take the minimum value 0. And how many deaths took place between 0 and 54.7. That's my first class interval. My second class interval is from here to this. And since I don't want that to shift, I will just put a function. And that gets fixed with, you can see that it's got locked with $J$. So that will not trip down. So I've got 100 observations. So let me take this down 100 times. So it has to come to 5476. The 100 is a lot. It's a little more. 5476. Yeah, that's my. So I'm now going to put this into a distribution because I can't visualize it unless I have it into a distribution, right? To stack this into a distribution, you can do it in Excel. I'll have to first create the class interval. So class interval is from 0 to 54.76, little above 54.76. I'm just showing you this. 54.76. This is how we read this, okay? Little above 62. So it's from 64.76 to 109.5 to so on and so forth till the end. So to fit a distribution in Excel, first create the class intervals. So these are called the class intervals. Okay, and these are called the frequencies. Okay, these are called the frequencies. So to fit it in, to fit a frequency distribution in Excel, select the range adjacent to the class intervals. Select the range adjacent to the class intervals. Then keep the selection on and type equal to frequency. FREQUENCY. Open a bracket and then it will prompt you. It's asking you where is the data. Since I'm dealing with data on debts, so I'll select it from here to here. Right? Then I put a comma. And then then it's asking me, the next question it asks me is, what is the bin range? The bin range is another name for the frequencies. Sorry, be right at the top. Yeah. So it's asking me what is the bin range. So I'll put a comma and select the bin range from here till the end. Close the bracket. And as usual, remember it's Control Shift Enter. Okay, there's a Control Shift Enter. And it's given me the distribution. So distribution is highly skewed. As you can see, the large number of debts are very, very few. So I think I have to reclassify this thing. So I will just have another distribution. I will have, I'll take the minimum value and I have increments of 10. Because you see, there's more than increments of say 10. Right? So 10. So I have 10. Then equal to this plus 10. 20. I'll drag it up till 100, up till maybe 200. 200. And anything more than 200, I will consider that as my class interval. So now again, I'm going to fit a distribution. So equal to, into frequency. So frequency. So I'm now going to take the data, which is debts, right, comma. Now pick up the class intervals, close the bracket, Control Shift Enter. Yeah. So I seem to have got a little better distribution, but I see the distribution is highly skewed. So maybe I can do that again a little differently. I will start with increments of 5. I will start with increments of 5. Up to 200. So follow the same procedure. Select a blank column of time column. equal in size to the class intervals, and let's start with frequency. Frequency, open a bracket, then it's asking for the data. The data is from here to here, comma, then ask for the class intervals, which are also lined up over there. So I'll select that. Right. And Control Shift. Sorry. Close the bracket. Control Shift. Control Shift Enter. Okay. So we got a distribution again, highly skewed, highly skewed, highly skewed. And now let us look at the plot. So I will select these two columns and go in for an XY plot. So I'll go to Insert, and I get an XY plot over here, and then I'll go for a line. So you can see it's a highly, highly skewed distribution with number of deaths. You know, and then on a day, the number of deaths are very, very less. So let me just break it down a little more, and let me say 4, 3, 2, 1, and 0. Frequency, data, close the bracket, bin range, comma, control, enter. So now we've got the distribution. Now you got a distribution. Again, it's a skewed distribution, highly skewed distribution, with the number of 0 deaths being taking the largest number. And you can see that that is distribution. So if I want to convert this into a probability distribution, I will divide each frequency by the sum of all the frequencies. So I will calculate as equal to this frequency divided by sum from here down to the bottom, close the bracket. So 86% probability that number of deaths would be 0. There is a I'll just fix this because otherwise it will start running away. So it's 86%. There's just a 4% probability that there will be 1 death per day. And there's just a 2% probability there will be 2 deaths per day. And this way we can find out the probability. Right? So before we start working with the data, what we do is we go and calculate the mean and the variance. Right? We will go and calculate the mean and the variance of the series. Okay, so now first let me carry in Excel, you can do it with the average. In Excel, we can do it with the average, so we just go to equal to, and yeah. So we get a mean like this, and we get a standard deviation, a variance. I can take standard DEV, open a bracket, and select the range. Okay, so we get a mean of 10.49 and a standard deviation of 157.4, which only goes to show it's a highly skewed distribution. And of course, we have to this thing. So that is what you do. So the first thing that you do in a distribution is you visualize it. The first thing that we do in a distribution, we call it a frequency distribution, we visualize. We can just visualize the distribution looking at the graph and then take a call on what type of distribution it may be. So we'll come to that later. So we're talking about discrete distribution. A discrete distribution displays the probabilities of outcomes of a random variable which have finite values and is used to model a discrete random variable. This distribution, these distributions are defined. So you define the distribution through what is called as a probability mass function. So this is something that you have to remember. The probability mass function is typical of a discrete distribution. Probability mass function. I'll explain what that is. The probability mass function, or PMF, calculates the probability that a random variable will assume the one specific value that is being calculated is the probability of a particular value x. Like I said, what is the probability there will be no deaths in a year? We got a probability of 86%. An example of some graphic representations of discrete distribution is displayed next. For any value of x in the discrete framework, there is one probability that corresponds to the specific observation, as you can see over here. So this is the probability of this value. This is the probability of 3. This is the probability of 4. This is the probability of 5. This is the probability of 6, and so on and so forth. So since it's a discrete distribution, you don't get values in between. So you get only for 2, you get for 3, you get for 4. So you use discrete distributions when the data is discrete, right? When the data is discrete, as in this case. As in this case. So as against discrete distributions, here what are called continuous distributions. Probabilities for the outcome of random variables with finite values and is used to model the continuous. So whenever the values are infinite, okay, you use continuous. So discontinuous distributions are distributions which give you the probabilities of outcomes if a random variable has infinite values and is used to model a continuous random variable. Random variables are uncountable, and the probability of a continuous random variable at any specific point is 0. Continuous distributions are typically described by probability distribution functions. So please make a note of this. Here it is a probability mass function. Here it is a probability distribution function. So the probability distribution function characterizes the continuous distribution. The probability density function is a function that is used to calculate the probability. So from the probability distribution function, we get the probability density function. It's a function that is used to calculate the probabilities that a continuous random variable will be less than or equal to the value that is being calculated. In other words, probability that x will lie between a and b, probability that x will be less than b. So this is what is called as a probability density function. So you will see that as we go along. So this is what a continuous variable looks like. It has all kinds of values. It is not discrete as in the earlier case. So it can take any conceivable value. Now, what do you mean by expected value? Now, expected value is very important in distribution theory because expected value is nothing but the mean. Each distribution, continuous or discrete, has different formulas to calculate the expected value or mean of the random variable. So you have to multiply the x value by its probability, which you calculate from the distribution, and then get the mean. So the formula for expected value is probability of x into x divided by summed up. So summation of probability of xi into p of xi gives you the mean. Another term to describe the expected value is the first moment. You also call it the first moment. It is important to remember that the expected value of a value is the value that one expects a random variable to be, which is the mean. So that is your expectation. When you calculate, when you talk about an expected value of prices, you're referring to the mean price. So because it's, in other words, expected value is what you expect it to be, and what you expect it to be is best summarized by the mean. Then you have another term which you've already come across, which is called variance. Each defined random variable has a variance associated with it. This is a measure of concentration of the observations within the random variable. So we try to see how packed the values are around the mean or how dispersed they are. So for that we calculate the variance. So this number will give us how far the spread of observations are from the mean. How far the value is from the mean. So the variance of a constant is zero. So if the variable has no variation, then the variance will be zero, because the mean of a constant is equal to the constant itself, and there's only one observation, and that is exactly the mean. So the standard deviation is a So the standard deviation is useful to the standard deviation is derived from the variance. It is also very useful and is equal to the square root of the variance. When calculating the variance, the idea is to calculate how far each observation of the random variable is from the expected value and square it. Then take the average and then take the square root. And that gives us the standard deviation. Very often in practice, we work with the standard deviation rather than the variance. So they are related. Okay. Now we come to the probability density function. As I told you, probability density function is relevant for continuous distributions. So distributions are often described in terms of their density or density function. So the density function describes the distribution, its shape, everything. Everything about the distribution, its characteristics are all captured by the density function. Two types of density functions. Two types of density functions are the probability density function and the cumulative density function. So you have two types, and the probability density function calculates the probability of observing a given value. Cumulative density function calculates the probability of an observation equal to or less than a value. So it's both related. One is the cumulative of the other. So once you calculate the density function, you cumulate it and you get the cumulative density function. Now, it's very important for us, particularly when you're using distributions in real life, we have to fit the distribution. We have to fit the distribution. So when you work with data to fit a distribution, first we start with the raw data and answers 4 basic questions about the data that can help us in the characterization. The first relates to whether the data can take on a discrete value or whether the variable is continuous, that we know earlier. Whether a pharmaceutical drug gets FDA approval or not is a discrete variable, but the revenue from the drug represents a continuous variable. So that's the first thing. You have to first decide whether the data is discrete or whether it is continuous. So in the example that I gave you about the deaths in COVID virus, you know upfront that the data is discrete, and therefore you cannot fit a continuous distribution. The second looks at the symmetry of the data, and if there's any symmetry, in which direction does it lie. So first we look at the data, whether it is discrete or continuous. Then we look at the symmetry of the data, whether it's symmetric or not. And if it's not symmetric, the extent of its asymmetry. So the third question that we ask is whether there is an upper or lower limit in the data. This is very, very important, because unless you know the limits of a data, of a distribution, and the limits of a data that a distribution requires, you cannot fit the distribution. Very often you will be making error. So data on revenues cannot have a lower value than 0. So 0 will be the lowest value, and the other operating will be the lowest value. But when it comes to operating margins, so the lower value will be 0. For revenue, the lower value will be 0. But for profit, the lower value can be less than 0. It can be negative. Okay. So similarly, the margin cannot exceed 100%. So these are some things that you should remember. The final and the related question relates to the likelihood of observing extreme values in the distribution. In some data, extreme values occur very infrequently, whereas in others they occur very frequently. So extreme values are very important, particularly when you're doing modeling of risk. Like for instance, when you're studying the stock market, In the future, you will definitely have the period that we are now experiencing, coronavirus, where the index fell from 12,000 all the way down to 8,500 to 8,800. Now, this is definitely an extreme value, which you will come to know as you go later on in life and later on when you study this. So, what is a probability? Probability statements describe the likelihood that a particular value occurs. Like I gave you, 86% is a probability that there will be zero deaths in a day, based on historical data. The likelihood is qualified by assigning a number from 0 to 1. So the probability, we rate to convert it to 0. It lies between 0 and 1 set of values, or the percentages from 0 to 100. Higher numbers indicate that the set of value is more likely to occur. We'll go back to this example. And from this example, we can see that the probability that there will be zero deaths is 86%. The probability that there will be one death per day is 4%. We can just convert this into, just put a control 1 and I'll convert it to percentages. Right? Now you can interpret, it's easier for you to interpret. The probability there will be one death in the world is 4.85%. The probability that there will be 2 deaths per day is just 2.17%. The probability that there will be 3 deaths is 1.45. The probability that there will be 4 deaths is less than a percentage. Probability that there will be 5 deaths is less than 0.4. And the probability that there will be 10 deaths will be 1.8. And the probability, so this is the probabilities that we get, and we can cumulate it and we get the cumulative. This is the probability density function, and the cumulative density function is by accumulating it. So I get this, and then I add this to this, this to this. So the cumulative is cumulative, and so on and so forth. You'll notice that the numbers keep increasing. I'll just take it to 10. Okay. So this gives me the cumulative density function. So what I can say is in 96.44 cases there will be less than 5 deaths a day in the world. So this is how we use the probability density function. So this is basically what this slide is all about. And now we get straight into the details of a discrete distribution. So a discrete distribution is one where the variable takes discrete values. They are countable. And when the data is of this type, then you have certain distributions which you use to fit this data. So the important discrete distributions are, you should know this, these are the important discrete distributions: the binomial distribution, the Poisson distribution, the geometric distribution, the hypergeometric distribution, the negative binomial distribution. There are many more. These are some of the important ones that you should know. Let us take them one at a time. What is a binomial distribution? A binomial distribution can be thought of as simply the probability of a success or failure outcome in an experiment or survey that is repeated multiple times. The binomial is a type of distribution that has 2 possible outcomes, and that is why you have the prefix bi, meaning 2 or twice. For example, tossing of a coin has only 2 possible outcomes, heads or tails. And taking a test will only have 2 outcomes, that is a pass or a fail. So as I told you, every distribution is characterized by its probability mass function if it is discrete. So if it is discrete, this is the probability mass function. N factorial divided by n minus x factorial into x factorial into probability of p into p raised to the power of x into q raised to the power of n minus x. Now px is the probability, binomial probability. X is the total number of successes. Okay, so I'm interested in successes, pass or fail, heads or tail. P is the probability of that success, and n is the number of trials, right? Now supposing you're doing, a coin is tossed 10 times. then n is 10. X will take the value 0. No, X will take the value 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which are possible outcomes? Here the probability here we are talking about, we are tossing the coin. So it can either be head or tail. So you can get one head in the 10 tosses, you can get one head. You can get two heads, then 8 tails. Or first you can get no heads at all. Technically, if it is a bias coin, you can get no heads, then 10 tails. Or you can get one head, 9 tails, two heads. So we are only interested in the number of heads because that is a positive event. So what is the probability of getting? Now I want to know what is the probability of getting exactly his 6 heads. So I will substitute it into this formula. Now n is 10 factorial. Now I will first say what is the probability of getting. Here I'm interested in getting exactly 6 heads. So it will be n factorial will be 10 factorial into 10 minus 6, which is 4 factorial, into 6 factorial, into p, which is already known. Probability of success is 0.5. So 0.5 raised to the power of 6. Q will be also 0.5. Tails can also be 0.5. Raised to the power of 10 minus 6 will give me the probability in a binomial distribution. So the binomial distribution must also meet certain form. The number of observations or trials is fixed. So the number of trials you're going to do is fixed. You can figure out the probability of something happening if you do it in a certain number of times. If you toss a coin once, your probability of getting a tail is 0.5. If you toss a coin 20 times, your probability of getting tails is very, very close to 0.5, 50%. So each observation of the trial is independent. This is very important. So the first tossing of coin should not be influenced the next tossing, which is quite true in a tossing of an unbiased coin. In other words, none of our trials have an effect on the probability of the next trial, which I explained to you earlier. Okay, so now let me show you this example in Excel. Take another sheet. So we know that n is equal to 10. Capital X is equal to 6. P, probability of success, is equal to 0.5 by default because tossing a coin will be 0.5. And obviously PQ, which is 1 minus P, is also 0.5. And now we can find out the probability of X equal to 6. Okay, so X is equal to 6. We want to find out X equal to 6. Okay, the X equal to 6. Now how do I do it? So we'll go back to the formula and revisit the formula. Yeah, so n factorial. So it's 10 factorial. In Excel we can do it very easily. As combination. No, we can do it, fact. Factorial, need an equals. Probably it's only fact. Yeah, fact is enough. Factorial 10. I'll do it in parts. Okay, that's the first part. Then we'll go to the second part of the formula, which is n minus x factorial into x factorial. N minus x factorial, that is equal to FACT n minus x factorial okay, that's the second part of the formula, and multiplied by x factorial. 6. Okay, multiplied by p raised to the power of x, q raised to the power of n minus x. So p raised to the power of x, p raised to the power of x into q raised to the power of n minus x. Close the bracket. Now we are ready to calculate the probability. So the probability is the bracket. So this divided by the product of this into this. So we got the first term multiplied by p raised to the power of q multiplied by q raised to the power of n minus x. So this whole thing should be covered into a bracket. So we've got what we want and we get a probability of 0.25. The probability that you'll get 6 heads in a toss of 10 coins, the probability that you'll get heads 6 times is 0.2. Now I will complete this for you. What is the probability that you will get no heads? What's the probability you get 1 head? What's the probability you get 2 heads? What's the probability you get 3 heads, 4 heads, 5 heads, 6 heads, 7 heads, 8 heads, 9 heads? What's the probability you get all heads? So we can use the formula here directly as equal to factorial n divided by, in bracket, let's check the formula once more, factorial n minus x into x factorial, n minus x, n minus x, n, I'll fix this, x into x into p, I'll fix it, raised to the power of x into q. Also I'll fix it, raised to the power of, in bracket, n, which has to be fixed, minus q, will give me the probability in its entirety. Into factorial So now if I drag it, I will get all the probabilities. check the formula once more. I'll do it once more. Equal to fact. So open a bracket. Fact 0 divided by n minus x in fix it minus x into fact x into q p. If I need to fix it, raised to the power of x into q, again needs to be fixed, raised to the power of in bracket n minus yes. No, there's still a mistake. This is going wrong, something wrong. Okay. I'll do this again, I'll do it individually. First I will do the first part. Equal to factorial 0 divided by factorial 10 minus 0 into the first part. Okay, this is the first part of this calculation. Then I'll do the second part. So it is p raised to the power of x q raised to the power of 10 minus x. Okay. So it will be this into this and all the three put together. Right. Yeah, now it has come. As you can see that 5 has the highest value, it progressively decreases and progressively decreases. So the highest probability is obtained from this. So from this I can find out the individual values. So it will be probability into n. I'll fix it because it should not shift. So you get the values. The values progressively decrease. So this is how the probabilities are to be calculated using the binomial theorem. Binomial distribution. So keep in mind the formula and how the probabilities are to be calculated. Okay, so now we've got the binomial distribution. Now we move on. So an example, many instances of binomial distribution can be found in real life. They use binomial distributions a lot to decide life tables. So in fact, they would, they do a distribution of deaths with age. So they have a history of deaths with age, and then they find out this. I can try to show you that also. We can now go back to this example. We can go back to this example on the coronavirus. Okay, and then we shall decide. Okay, now I want to find out what is the death by latitude and longitude. Okay, so I will just use a pivot table to simplify the process, as I should have done it the right way. Okay, I will find out what is the minimum lot, what is equal to min latitude so minimum latitude in the data is this, and the maximum latitude would be this. Right. So the minimum latitude, oh god. Something wrong with the data. You don't get a minimum latitude minus 41. I presume it's a mistake in the data. We'll just check it up. There are many negative latitudes. Okay, so probably it's right. Okay, that's the minimum. So let us make this into 10 class intervals. Maximum minus minimum divided by 20 class intervals, or 10 class intervals. Right? So I've got a gap of 11. So I will now take the minimum latitude, fix it. To that I will add the class interval, which I'll also fix, and then I will keep incrementing it by the class interval, which I'll fix with F4, and I'll drag this down till I get 72. I get 72. This is rather easy. Now I want to find out how many deaths are there in this latitude. So equal to so I'll try to find out in this latitude how many deaths are there. Okay. So I'd rather do it in a filtered way. I don't think I have an option in Excel to give you that value. You can do a count if sum if. Okay, I think I can do it here. I'll do it directly through a pivot table. I will go to insert, I will do a pivot table, and I'll say OK, and you'll understand this a little better. So here I will take the latitude, right? And here I will take the deaths, right? And then I've already defined the latitudes here. Less than minus 30, less than minus 30. So minus 30 would come somewhere here. Minus 30, yep. Okay. And I go to group. Minus 30. Group the selection. Group the selection. So that is up to 30. I'll say less than 30. There's also frequency distribution, right? Then we go to the next one and I'll say till minus 18. From here to minus 18, sorry. Till minus 18. So here I will come here. Group minus 18, we'll go to the next this thing and we go to minus 7. The next group is still minus 7. Group minus 7. The next group is still 3. Group. The next group is still 15.27. The next group will be 26.6. The next group will be till 37.38. The next group will be till 38. next group is 38, right? And the next group is 49. And the next group is 61 and then 72. 61 and 72. Okay, so we have got all this. So we can remove this lat 2 and we get a nice neat distribution group wise. So this is group 1. There's one group that got left out. There it is. Okay, now we got the groups. And now you can see that most of the deaths, okay, this it will not done too well. I mean, you can just. So this is group 11. Okay. From this we can conclude, so group 2 will come here. Okay. So now we have group 1. I will get the groups here, then you'll for better understanding of the data. Because there are formulas. Okay. So these are the groups. These are the frequencies. Okay, you're working with discrete data and we are just looking at it in terms of latitude. Now we find out that most of the deaths, now what's the probability of deaths when the latitude is less than 30 degrees? So it is this divided by sum of all the values put together, fixed it with F4, close the bracket, right, and enter. So that's a probability. These are the probabilities that people would die we'll convert it to percentage. What's the probability that people would die in the less than 30 degrees latitude? 0.06. What's the probability that they'll die with less than 19? So less, and you find from this that it is in this latitude, that is 26 degrees latitude, between 15 and 26 latitude, that the death is the highest. So this is the information that you want to derive from a distribution which you could not have done either way. So if I take a plot of this, I can take a plot of this data because this data is good. I go to insert and I go to this option, and I go to this option, and it gives me a nice distribution, peak distribution. This is a distribution, fairly normal in terms of latitude. So on the x-axis you find latitude, and you know most of the deaths take place in the latitude 15 to 26 degrees. 15 to 26 degrees latitude, most of the deaths would be taking place. So just out of curiosity, you can just go and say latitude Bangalore. Then the latitude is 15 Bangalore latitude is 12.97 degrees northeast. So Chennai is 13, Hyderabad is 17, Delhi is 28. Latitude, longitude, yeah. Latitude, longitude, yep. So it is 13. Bangalore, Chennai is 13. Bangalore is 12.68. So strictly, we are outside the range of the critical range of deaths. So deaths don't take place so much in this range. As you say, 15 to 26 is high. Yeah, 15 to 26. So yeah, Bangalore comes really less than that. We come less than that. We come into this range. No, we come to this range. 12 to 15. We are in this range. Yeah, really, we are really in this range where the probability of death is less. It is only in latitudes 15 to 26, which Delhi comes within that. The latitude, you could see that. Delhi comes within that, 28, 28, 15 to 20. Okay, there's a little bit, 26 to 28. So Delhi comes here. Bangalore comes really, Bangalore comes strictly in the 12. So it'll be in the this category. So 3 to 15 degrees latitude, where the death rate is very, very low. So this is one of the great applications of about the distribution theory, because it tells you. Now this kind of fits a normal distribution. It's discrete though, but we can show it like a normal distribution. Ideally, we should have shown it like this. We should have shown it like this with bars. We don't have that option anyway. It doesn't matter. Okay, so this is basically what we should have ideally done. Is we should have just shown it as a bar like this. So strictly, this is the distribution. This is the distribution. So there's a peak depth between latitudes 15 degrees to 26 degrees. So we are well out of that 15 to 26. Bangalore is out of that 15 to 26. The critical one is from 15 to 26. So we are out of that 15 to 26. We are 12. So anything more than 15 would definitely be 15 would be a problem. So Hyderabad, yes, Hyderabad is in that range, critical. Delhi is out of that range because it's in 28. So Hyderabad, central India becomes a little vulnerable to this distribution. So this is one of the very useful applications of distribution theory. We'll continue. So many binomial distributions. So you want to find out what is the death rate. So that's a binomial distribution. So every category, look, death rate, that is probability. So it gives you the probability. And from this you can find out what is the probability in each group. So I know the probability of 0.5. So everybody in this group, minus 18 to minus 17, what is the probability? This thing. Here the probability is 0.6. So what is the probability of 1 death, 2 deaths, 3 deaths, 4 deaths? So each category follows a binomial distribution. And that is one of the very useful applications of binomial, used in life tables, used for constructing life expectancy, so on and so forth. So, for example, if a new drug is being introduced to cure a disease, it either cures the disease, if it's successful, does not cure the disease if it's not successful. So the probability should be known, and you can find out what's the chance that it will clear. It'll clear. If you purchase a lottery ticket, again, anything you can think of that can be a success or a failure can be represented by a binomial distribution. So that sums up binomial distribution. Now we move on to Poisson distribution. Now Poisson distribution is the distribution of rare events. Poisson distribution is a distribution of rare events. So it is a tool that helps to predict the probability of a certain event from happening when you know how often it has occurred. It gives us the probability of a given number of events happening in a fixed time interval. So when you're doing quality control and you're examining a material to find out how many defective, like could be lots of bulbs, it can be lots of 100 bulbs, and you randomly check and find out how many defective bulbs are there. The chance that a lot will be defective will be very rare, maybe 2 in 100, 3 in 100, 4 in 100, and then when you want to predict the probability, you normally use a Poisson distribution. So Poisson distribution is a tool that helps to predict the probability of certain events which happen when you know how often the event has occurred. It gives us the probability of a given number of events happening at a fixed timetable, at a fixed interval of time. The average number of major storms in your city could be 2 per year. So, what is the probability that will be exactly 3 storms will hit your city in a year? Can be calculated using a Poisson distribution. So, it means that you have a history of information. You can also use information on rainfall failures. So, in the last 30 years, the probability that rainfall in 20% of the cases the rainfall has failed. So, you get a probability of 0.2. So when you have this probability, you can calculate what is the probability that there will be 1 year of for failed rainfall, 2 years of failed rainfall, 3 years of failed rainfall using a Poisson distribution. Okay, the interesting thing about a Poisson distribution, its mean and its variance will be the same. So here, the probability mass function is not distribution function, mass function. Of a Poisson distribution is given as e raised to the power of minus mu into mu raised to the power of x into x factorial. So factorial is factorial. Mu is the expected number of occurrence, 2, 3, 4. It's sometimes written as lambda. It's also written as lambda. So this can be written as mu raised to the power of lambda. Lambda raised to the power of x. Lambda raised to the power of x into x factorial. It's a rather simple formula where mu is x, the number of occurrence, sometimes written as mu, sometimes called the event rate or the rate of the parameter. Now we can go back to the same example. The average number of storms that hit a city is 2. So in this formula, so e raised to the power of minus 2 into 2 raised to the power of x is equal to, what's the probability of 3? No, we want to find out 3. So we shall use it in Excel. So we'll come back here. So probability of no storms, probability of 1 storm, 2 storms, 3 storms, 4 storms, 5 storms. Okay. So probability of 3 storms is calculated as equal to e raised to the power of. Now e is a natural exponent. In Excel it's just the exp, or it takes a value 2.71828. So e raised to the power of 3 e raised to the power of 3, 2. Average is 2, no? E raised to the power of mean into 2 raised to the power of into 2 raised to the power of 2 raised to the power of 3. Two raised to the power of 3. So e raised to the power of 2 into 2 raised to the power by 3 factorial divided by fact 3x. So the probability is sorry, I made a mistake. Please see the formula again. E raised to the power of minus lambda. That's a mistake I made. So e raised to the power of minus lambda, lambda is 2, into lambda raised to the power of 3 by 3 factorial gives us. So probability that there will be 3 catastrophes in a year when the mean is 2 is 0.18. So let us calculate what is the probabilities of each one of these. So this will be equal to exp raised to the power of minus 2, this is of course a constant, into 2 raised to the power of 0, 0, yeah, divided by factor 0. So probability that there will be no this thing will no catastrophes will be 0.4. The probability that there will be one catastrophe will be 0.27. The probability that there will be two catastrophes, which is most likely, is 0.206. The probability there will be 3 more. 1 and 2, of course, seems to be quite high, and the probability diminishes as you go along. Correct. So the probability that there will be, sorry, it should have been calculated here. Yeah, that's true. D30, yeah, by 30 factorial, yeah, correct. 2, 31, yeah, 31 by 31 factorial. 3 is 0.18, and the probability of 4 will also be 0.18. Oh, sorry. Choose this formula. Okay, it progressively comes down. The probability of 5 calamities will be 0.5. So that way you can find out the probability. Now, another thing I just mentioned before I move on, you can calculate once you know the value of P and Q, you can calculate the mean and standard deviation, mean and variance of the data that follows the binomial distribution. So mean is P into Q. So the mean of this distribution is 0.5 into 0.5, which is equal to 0.25. The standard deviation is NPQ. So it is 0.5 into 0.5 is 0.25. 0.25 into 10 is 2.5. So the standard deviation is 2.5. The mean is 0.25. So you can calculate this as, so the mean is N into P into Q. The standard deviation is N into P into Q, where N, P and Q have been defined. Now we move on to the hypergeometric distribution. So the hypergeometric distribution is a probability distribution that is very similar to the binomial distribution. In fact, the binomial distribution is a very good approximation of the hypergeometric distribution as long as you are sampling 5% or less of the population. So if your study covers a population of maybe 10,000 people, and if your sample which you're used to do the study is less than if your sample is less than 5% of the population, then binomial distribution is a good approximation of the hypergeometric distribution. Okay, so when you have a small sample, then you can go for a binomial distribution rather than a hypergeometric distribution. Hypergeometric distribution is only when you use large data. The probability mass function of the hypergeometric distribution is here. So this is K, C, K, N minus K, K minus K, and N. So what is K? K is the number of successes in the population. So you should know the population figure. And the K is the number of observed successes. How much do you want to see? N is a population size, and N is a number of. Now, what you're saying, the problem can be worded like this. A small voting district has 110 females and 95 male voters. A random sample of 10 voters, in a random sample of 10 voters, what is the probability that you will get 7 voters will be female? So this is the question. Okay, so in a small voting district with 101 females and 95 male voters, a random sample of 10 is drawn. What is the probability that the sample will have exactly 7 voters and exactly 7 voters who will be female? Here also you can see there are 2 categories. Okay, now let us go back and do an example. So males, females, males, 96. So total number, which is capital N, the total number is equal to female plus male. Female plus male. The sample that you're drawing, which is denoted as small n, is 10. My question is, I want to find out when there are exactly, if I draw a sample of say 10, what is the probability that 7 of them will be females? So 7 of them will be females. So because I write it as small k is 7. Now recall the formula. We can do it in parts. First, let us take this part. This is KCK. KCK. So it's an example in combination. So equal to COMB and just see how combinations are done. I can just go over here and type combin. Yeah, the word is combin. So first I'll make it, there are two, equal to COMBIN, open a bracket. So my first combination, as you can see over here, is KCK. K. This is K. C combination of small k. My first part. My first part of my formula. This is KCK. Now this is n minus k into n minus small k. Again a combination. So I'll do that here. So equal to COMBIN, open a bracket. So n minus k, I'll do a small bracket here. N minus k, comma, minus small n minus k into small n minus small k. This is the second part of my combination. Okay, the second part of my combination. And the third part of my combination is NCN, which I'll do here as equal to COMBIN NC small n. So you can see I've broken up the formula into three parts. The first part is, yeah, you can show them to you simultaneously. The first part is KCK. So this K. First part is KCK. The second part is n minus k, and small n. So n minus k, and small n minus k. That is this part. And the third part of the combination is capital N C N. N C N. So the three parts, I'll combine it together. So that will be equal to this into this divided by this. I get a value of 0.13. So in this example, the probability that they will be in a given the population of 101 and 95, if you draw a sample of 10, then the probability that in that sample there will be 6 females is 0.13. So that is a hypergeometric distribution which we've been discussing so far. Right? So that's a hypergeometric distribution. So the example that we worked out, we get a value of 0.13. The same thing has been shown over here. And now we move on to the third discrete distribution, the fourth discrete distribution, and that's called the negative binomial experiment. The negative binomial distribution, I'm sorry. The negative binomial distribution. The negative binomial distribution. Okay, so if the following 5 conditions are true, the experiment is binomial. So for binomial, so if there is a fixed number of n trials, if the number of trials are fixed, and then each trial is independent, only 2 outcomes, success or failure, and the probability of success of each trial is a constant and is a random variable, really measures the number of successes, you normally go for a binomial. So the example is, take a standard deck of cards, shuffle them and choose a card, replace the card and repeat 20 times. Right? So a fixed number of red trials. 20 times. Y is a number of times, Y is a number of aces you draw. So you find out how many, so you take a set of cards, you shuffle it, choose one card, see whether it is ace, you put it back, shuffle it again. So after how many trials do you get a finally ace is given by Y? Okay, if Y is given by Y. And then, okay, so that's it. A negative binomial distribution is also called as a Pascal distribution. It is a discrete probability distribution for random variables in a negative binomial experiment. The random variable is a number of repeated trials, that is X, that produces a certain number of successes R. In other words, it is a number of failures before you get a success. So X is a number of times. How many times did you pull out a card before you get an R? Is actually the X. So it's actually a number of failures. This is the main difference between a binomial distribution and a regular binomial. This is the difference between a binomial distribution and a regular binomial distribution, negative binomial. Sorry, difference between from the negative binomial distribution and the regular binomial distribution. Binomial distribution, the regular binomial distribution. You're looking at a number of successes. With a negative binomial distribution, is a number of failures that you count. How many times did you fail before you got the right value? So then again you have a probability mass function which is written as x minus 1 combination r minus 1. Probability raised to the power of r into 1 minus probability raised to the x. Very similar to the binomial distribution, where x is the number of trials. Where x is the number of trials and r is the number of rate of success. Okay, so the mean is also always calculated by r successes divided by trials. It's given by the mean. So where r is the number of trials and p is the probability of success of any one trial. Example, if you are surveying people exiting from a polling booth and you ask them if they voted for a particular candidate, the probability P that a person voted for an independent candidate is 20%. So we know your vote share. What is the probability that 15 people must be asked before you can find 5 people who voted for the candidate? And the probability you will have to ask 15 people to get 5 positive votes is the probability that you're looking for. So in this example, your success rate is 5, your trials are 15. So if you go back to this example, x is 15, success rate is 5, and you can get the probability once you know the probability of success. Okay, so you can now let us go and solve this. Okay, we take this formula And we will solve this negative binomial distribution right here. So that's a formula for a negative binomial distribution. And now, so the data is given, we'll just stick to that. We'll just stick to the data that has been given. You are serving people who are exiting from a private. So this is the problem in the question also. Okay. So probability. So x is equal to 15. We'll just go back just to recollect. So x is a number of trials. X is a number of trials. So 15 people. And success rate is 5. Okay. So we can go back. So x is equal to 15. And R is a success rate is 5. The probability is 0.2. Probability is 0.2. And now we can calculate it as in 3 parts. First I'll do the first part. Is x minus 1. X equal to, open a bracket, x minus, equal to combination COMBIN, open a bracket, open a second bracket, x minus 1, comma, into r minus 1. Open another bracket, r minus 1. Close the bracket. So that's the first part. Okay, you can see that, no? Combination E23, yeah. E23 minus 1, E24 minus 1 is first part. Then the second part is the probability, which is 0.2 raised to the power of R. And the third part is equal to 1 minus b raised to the power of x minus r. Okay. Equal to, I'll do that again, 1 minus b raised to the power of x minus r. Okay, I'll combine the three things to get the probability, which is equal to this into this into this term. And we get a value of 0.03. So the probability of this solution, this problem, is 0.034, which is the value I've got over there. Calculated rather easily. 0.034 or 3.4%. So coming back to the problem, probability that P persons, supposing you know the voters, what is the percentage of voters for a particular party, and you want to find out when you choose 15 people, and you want out of that 15, you want 5 people to be people who are voting for that particular party, then if you do this calculation, you'll get a value of just 0.34, which is a very remote possibility. And that is how the negative binomial distribution is very useful when you're doing retail sales. How many people come to the shop visiting before the first guy purchases the product? How many people visit your website before the person buys your product from your website? Very, very useful in present day analysis, distribution, negative binomial distribution. Particularly, you can predict when 100 people visit, how many, when will you, how many, what's the probability that 20 people will buy? And that these kind of things can be done. It all depends. So these distributions, you have to work a lot with it, because the calculation is very easy, like I told you in the very beginning. Once you know the probability mass function, it's only a question of plugging in the values and finding out what is the probability. So therefore, this is how the probabilities are calculated. So these are all the probability mass functions. The cumulative probability functions, you can cumulate it and find it out. And I can just show you that with the distribution that we did earlier. Yeah. So you can find out for like this. You need to find it out for 15. No? 1, 2, 3, 4, 5. You can not only stick to this, you can do it for 1, 2, 3, 4, 5, and find out which is most likely. You can use it for that, and this is how the distribution functions work. Okay, so these are some of the important discrete distributions which are used in analysis. Got a lot of application nowadays, particularly in the area of web analytics and things like that. But you need to thoroughly understand what they really do. So next we move on to continuous distributions, which I will do in the next presentation.